Welcome to the AI Odyssey, unraveling the evolution of intelligence. I'm your guide, ready to embark on a fascinating journey through the history and future of artificial intelligence. We describe AI as one of the most significant technological developments of the modern era. From its theoretical inception, AI has transformed from an academic curiosity into a fundamental technology, reshaping industries and our interaction with machines. In this first lesson, we'll lay the groundwork, exploring what AI truly is, its historical roots, and the initial sparks that ignited this incredible field in its genesis period, from the 1950s to the 1960s. Let's begin at the very beginning. So, what exactly is artificial intelligence? This can be defined as computational systems designed to perform tasks typically requiring human cognitive abilities, such as reasoning, learning, perception, language understanding, and problem solving. Unlike traditional software that follows predetermined instructions, AI systems adapt their behavior based on data analysis and pattern recognition. It's important to distinguish between narrow AI, which excels at specific tasks like playing chess or recommending products, and artificial general intelligence, or AGI, a theoretical concept where AI would match or exceed human cognitive abilities across all domains. Most AI we interact with today is narrow AI, but the practical definition has evolved from early symbolic reasoning to modern statistical learning from vast datasets. The very idea of artificial intelligence emerged from profound questions about the nature of intelligence itself. The primary motivation was to augment human capabilities, not to replace them entirely. A pivotal moment was Alan Turing's seminal 1950 paper, Computing Machinery and Intelligence, which famously posed the question, can machines think? This inquiry established the conceptual foundation for AI research and introduced the Turing test as a benchmark, evaluating whether a machine could engage in conversation indistinguishable from human dialogue. The vision included automating routine cognitive tasks, solving complex problems beyond human capacity, and creating intelligent assistants. It was about pushing the boundaries of what machines could achieve. Modern AI systems operate on several fundamental principles. Data serves as the primary input, providing examples from which systems learn patterns. Algorithms define the mathematical procedures for processing that data and generating outputs. And computational resources enable the intensive calculations required for learning and inference. The learning process typically involves training systems on large data sets to identify patterns, adjusting internal parameters to minimize errors. Unlike early AI that relied on symbolic logic, contemporary AI relies heavily on statistical methods and machine learning algorithms to analyze data and construct mathematical models. This approach has proven more effective for the complexity of real-world problems. The Genesis period truly began with the Dartmouth Conference of 1956, where the term artificial intelligence was coined by John McCarthy. Pioneers like Alan Turing, Herbert Simon, Alan Newell, and Marvin Minsky laid the theoretical groundwork, drawing from mathematical logic, information theory, and cybernetics. They envisioned machines capable of learning and adaptation. This era saw exciting early achievements, notably game-playing programs like Arthur Samuel's checkers program, which improved through self-play and eventually achieved master-level performance, demonstrating the potential of machine learning. Theorem-proving systems like the logic theorist also showed automated reasoning. These successes attracted significant investment and established AI's credibility. Despite this initial enthusiasm, first-generation AI systems faced fundamental limitations that would ultimately lead to a period of reduced confidence. As you can see in the visualization, one major constraint was computational resources. Early computers simply lacked the processing power and memory for sophisticated AI, limiting programs to toy problems. Another challenge was knowledge representation. Rule-based systems required explicit programming of all knowledge, proving brittle when encountering unforeseen situations. Their learning capabilities were also rudimentary, relying on handcrafted knowledge rather than true learning from data. Finally, the combinatorial explosion problem plagued many approaches. As problems grew, the number of possible solutions exploded exponentially, overwhelming computational power. These challenges would drive the field to seek entirely new approaches in later decades. We've journeyed through the foundational concepts of AI, from its definition to the visionary beginnings and the critical hurdles faced during its genesis period. We've seen how pioneers questioned if machines can think and established early benchmarks like the Turing test. We also acknowledged the limitations of early computational power and knowledge representation, which would eventually lead to a shift in AI methodology. These early challenges are crucial context for understanding the AI journey. In our next lesson, we'll delve into the era of expert systems, the challenges that led to the first AI winter, and the subsequent machine learning renaissance that set the stage for modern AI. Get ready to explore the exciting shifts from rules to data. See you then. Welcome back to our AI Odyssey. In our last lesson, we explored the foundational concepts of AI and its visionary but limited genesis period. Today, we delve into the next pivotal chapters, the era of expert systems from the 1970s and 80s, the chilling period known as the first AI winter, and the glorious machine learning renaissance of the 1990s, profoundly shaped by the internet and data revolution of the 2000s. We'll trace the fascinating shift from rigid rules to adaptive data-driven approaches and see how computational power and vast datasets paved the way for modern AI. Get ready to understand how AI learned to learn. The 1970s saw a significant shift towards expert systems. These systems captured human expertise in specific domains using rule-based knowledge. Think of them as highly specialized digital advisors. They had a knowledge base of rules, an inference engine for reasoning, and a user interface. Some prominent examples are Mycin for medical diagnosis, Dendril for chemical analysis, and XCon for configuring computer systems. These systems were successful in narrow, well-defined domains, demonstrating AI's potential for professional decision support and streamlining operations. But their rule-based nature would soon become a major limitation. Despite early successes, expert systems faced significant limitations that led to the first AI winter in the late 1970s and 80s, a period of reduced confidence and funding. The main culprit was brittleness. When systems encountered situations not explicitly covered by programmed rules, they would fail catastrophically. Imagine a medical system unable to diagnose a rare disease because its rules didn't account for it. Maintenance challenges also plagued large rule bases, making them expensive to update. Knowledge acquisition proved difficult, as extracting tacit human expertise was complex. Lastly, their limited learning capability meant they couldn't improve performance through experience. These constraints, coupled with overinflated expectations, taught valuable lessons about the need for more adaptable and robust AI. The 1990s marked a fundamental paradigm shift, the machine learning renaissance. This was a departure from explicit rules to data-driven approaches. Instead of telling the AI every rule, machine learning algorithms could automatically extract patterns directly from data. This offered several advantages, handling noisy data more gracefully and discovering subtle patterns that humans might miss. The increasing availability of larger datasets and improved computational resources made this shift viable. As you can see in the comparison, this was a move from programmed knowledge to learned patterns. This laid the groundwork for the AI we know today. This decade saw the refinement of crucial machine learning algorithms. Decision trees provided interpretable models, support vector machines offered powerful classification tools, and Bayesian networks allowed reasoning under uncertainty. A major advance was in handling sequential data. Recurrent neural networks, or RNNs, could process sequences like text by maintaining an internal memory of previous steps. However, they faced the vanishing gradient problem, struggling with long-term dependencies. The breakthrough came with long short-term memory, or LSTM networks, introduced by Hochreiter and Schmidhuber in 1997. LSTMs could selectively retain or forget information over extended sequences, solving the vanishing gradient problem and forming a foundation for later advancements in natural language processing. The 2000s ushered in the internet and data revolution, fundamentally transforming AI development. Web services generated a digital data explosion of user interactions, search queries, and social media activity. Digital content creation accelerated, providing vast multimedia training data. This era also saw crucial computational infrastructure advances. Graphics processing units, or GPUs, originally for video games, proved ideal for parallel neural network operations. Cloud computing democratized access to high performance computing, lowering barriers. We also saw data representation and processing evolve with tokenization and embedding techniques like word-to-vec, which captured semantic relationships in numerical forms. All this data and power were essential catalysts for AI's next phase. Machine learning truly achieved mainstream consumer adoption during this period. Search engines like Google incorporated ML to improve query understanding and ranking, profoundly impacting how billions access information. Online advertising systems leveraged ML for targeted marketing, creating massive economic value. Social media platforms used ML for content recommendation and engagement, shaping our digital interactions. Translation services improved dramatically, and e-commerce giants like Amazon used sophisticated recommendation systems to suggest products, driving sales and customer satisfaction. The document notes, the integration of machine learning into consumer applications established AI as an invisible but essential component of modern digital experiences. This widespread adoption set the stage for the next dramatic leap in AI. In this lesson, we've navigated AI's journey through the promise and challenges of expert systems, the crucial lessons of the first AI winter, and the transformative machine learning renaissance. We saw how the shift from rules to data-driven approaches, powered by statistical methods and the innovations of LSTMs, set the stage. The internet and data revolution provided the vast data sets and computational power necessary for AI's next leap. These shifts were vital in making AI an invisible but essential component of our digital lives. In our next lesson, we'll witness the dramatic deep learning and modern AI boom, leading directly into the exciting generative AI revolution that defines our present. Get ready for the AI capabilities that have truly captured the world's imagination. Welcome back to our exploration of AI's evolution. We've traced AI from its foundational concepts through the expert systems era, the AI winter, and the machine learning renaissance. Now we arrive at the most exciting and transformative period, the deep learning and modern AI boom from 2012 to 2020, leading directly into the generative AI revolution from 2020 to the present. This is where AI truly exploded into public consciousness. We'll explore how neural networks made a comeback, the revolutionary transformer architecture, and how it enabled large language models to create text, images, and more. Get ready to understand the technology powering today's AI marvels. The period from 2012 to 2020 witnessed a neural network renaissance, particularly for deep learning architectures. This was catalyzed by large datasets, powerful computational resources like GPUs, and algorithmic improvements. The breakthrough moment was AlexNet's victory in the 2012 ImageNet competition. This convolutional neural network achieved unprecedented accuracy in image classification, dramatically surpassing traditional computer vision. Deep learning architectures consist of multiple layers, learning hierarchical representations of data, meaning lower layers learn simple features, while higher layers combine them into complex patterns. This approach, combined with improved backpropagation algorithms, made deep learning practical for a wide range of applications and marked a revolutionary transformation in AI. A crucial advancement in this period was the development of attention mechanisms. Attention allowed models to selectively focus on relevant parts of input sequences when generating outputs. This was vital for processing long sequences, especially in language. Then came the game changer, the transformer architecture, introduced in 2017. Transformers eliminated recurrent connections entirely, relying solely on self-attention mechanisms for sequence processing. As you can see in the diagram, this design enabled full parallelization during training, dramatically reducing computational time and allowing for unprecedented scale. Multi-head attention further allowed transformers to attend to different types of relationships simultaneously, providing rich representation capabilities for natural language processing tasks. The transformer became the foundational block for the next AI revolution. Deep learning achieved remarkable success across numerous domains. Computer vision reached human-level accuracy in image classification and object detection, enabling applications in autonomous vehicles and medical imaging. A key milestone was AlphaGo's victory over Lee Sedol in 2016, demonstrating deep learning's potential for strategic reasoning in the complex game of Go. Speech recognition systems achieved near-human accuracy, enabling practical voice interfaces. And natural language processing tasks like machine translation and sentiment analysis saw significant improvements. These achievements captured public attention and drove substantial investment, proving AI could exceed human performance in specific, highly complex tasks. The transformer architecture directly led to the generative AI revolution, starting around 2020. This is characterized by foundation models and large language models, or LLMs, capable of performing diverse tasks without specific training. GPT models, or generative pre-trained transformers, pioneered this. GPT-3, released in 2020, with its 175 billion parameters, demonstrated remarkable few-shot learning. These models are pre-trained on vast amounts of diverse text, then fine-tuned. They exhibit emergent capabilities like mathematical reasoning or creative writing that weren't explicitly programmed but emerged from patterns in their training data. This scale and versatility redefined what AI could do. Generative AI capabilities extend far beyond just text. Multimodal content generation allows AI to create images, audio, and video from natural language descriptions, democratizing creative tools. Diffusion models emerged as a powerful approach for image generation, with systems like dall-e, Midjourney, and Stable Diffusion creating high-quality images from text prompts, often with remarkable artistic quality. You can request images in specific artistic styles depicting complex scenes. Audio generation systems create music, speech, and sound effects, while early video generation systems show potential for coherent motion and scene transitions. This has fundamentally altered content creation workflows across industries. Generative AI has seen rapid commercial adoption and significant social impact. In content creation, marketing teams use AI for personalized content, designers prototype visuals, and writers use AI for ideation. Software development is revolutionized by AI coding assistants like GitHub Copilot, which generate code from natural language, increasing programmer productivity. Customer service leverages LLMs for sophisticated chatbots. And in education, AI offers personalized tutoring and essay grading. The accessibility of these systems, often through simple text interfaces, has enabled widespread adoption by non-technical users, fundamentally altering how many industries operate and interact with information. We've covered an immense amount of ground in this lesson. We witnessed the deep learning renaissance and the resurgence of neural networks, culminating in breakthroughs like AlexNet and AlphaGo. Crucially, we explored the transformative power of attention mechanisms and the transformer architecture, which paved the way for foundation models and large language models like GPT, showcasing incredible emergent capabilities. We also dived into multimodal content generation, seeing how AI now creates images, audio, and even video, and its vast commercial and social impact across industries. In our final lesson, we'll delve deeper into understanding AI technology, examining its core components and learning paradigms, and crucially, tackling the contemporary challenges and future directions, including the critical ethical considerations like hallucination and bias. Get ready to wrap up our AI Odyssey with a look towards a responsible future. Welcome to the final lesson of the AI Odyssey, unraveling the evolution of intelligence. We've journeyed from AI's origins, through its various historical periods and technological breakthroughs, right up to the revolutionary generative AI of today. In this concluding session, we'll dive deeper into understanding AI technology by examining its core components and machine learning paradigms. Crucially, we'll confront the contemporary challenges and future directions, including the significant technical limitations and ethical considerations that demand our attention. Finally, we'll look ahead to the research frontiers shaping AI's future. It's essential to not only appreciate AI's power, but also to understand its nuances, limitations, and our shared responsibility in its development. Before we delve into challenges, let's briefly unpack the core components of AI systems. First, data is the foundation, providing examples for learning. Its quality and quantity directly impact performance. Second, algorithms define the mathematical procedures for processing data and learning patterns. Different algorithms suit different problems. Third, model architecture determines how information flows and components interact. Modern architectures like transformers are particularly effective. Finally, training procedures specify how systems learn from data, including optimization and evaluation. High-quality data and effective training are crucial for robust AI behavior. Machine learning encompasses distinct approaches to learning from data. As you can see in the chart, supervised learning uses labeled examples to train models, like classifying images or detecting spam. It requires knowing the right answers in the training data. Unsupervised learning discovers patterns in data without explicit labels, identifying hidden structures, such as customer segments or anomalies. Finally, reinforcement learning trains agents to make sequences of decisions by interacting with an environment, receiving rewards or penalties. This is how AlphaGo learned to play Go. These paradigms address different problem types and data availability, making them versatile tools in the AI toolkit. Despite their remarkable capabilities, current AI systems have significant limitations. A major one is factual accuracy and the hallucination problem. Systems sometimes generate plausible but incorrect or nonsensical information, which creates risks for applications requiring reliable data, especially in healthcare or legal advice. Reasoning capabilities, while impressive, remain limited for truly complex logical problems or multi-step tasks. Systems might sound correct but contain logical errors. Interpretability is another challenge. The complex black box nature of deep neural networks makes it hard to understand why a system made a specific decision, raising concerns for accountability. Also, adversarial examples show brittleness, where tiny, imperceptible changes to input can cause dramatic errors, raising security questions. These limitations highlight why human oversight is non-negotiable. Beyond technical limits, ethical considerations are paramount. First, bias and fairness. AI reflects biases in its training data, leading to discriminatory outcomes in areas like hiring or lending. Second, data privacy and security. Training data often contains sensitive information. This raises concerns about privacy breaches and intellectual property. Third, accountability and human oversight. If an AI makes a mistake, who is responsible? The ultimate accountability, as the document states, lies with the human user. Fourth, economic and social implications include job displacement and widening inequalities. Finally, environmental impact from the massive energy consumption required to train large models. As the content plan emphasizes, ethical considerations are inherent in AI development and deployment, requiring human oversight and accountability. Despite challenges, AI research continues to push boundaries. Exciting research frontiers include developing more interpretable AI models to understand their decisions. Robustness to adversarial examples is another key area, improving AI's reliability in real-world scenarios. Researchers are also working on reducing AI's computational footprint for more sustainable development. The quest for artificial general intelligence, or AGI, continues, though it remains a long-term goal. There's also growing interest in AI for science, using AI to accelerate scientific discovery, and human-AI collaboration to create symbiotic relationships where humans and AI augment each other's strengths. The document concludes with a powerful thought. AI has transformed from an academic curiosity into a fundamental technology reshaping industries, society, and human interaction with machines. The journey continues, and our responsible engagement is key. Congratulations on completing our AI Odyssey. You've gained a comprehensive understanding of AI's incredible evolution, from its philosophical roots and early symbolic systems, through the data-driven machine learning renaissance and the explosion of deep learning, to the current transformative era of generative AI. You now grasp the core components, learning paradigms, and critically, the significant technical and ethical challenges that define modern AI. Remember, AI's history is a story of continuous learning and adaptation, driven by overcoming past limitations. This includes addressing the hallucination problem and ensuring fairness. This knowledge empowers you not just to understand AI, but to engage with it critically and responsibly. The journey of AI mastery is continuous, and your informed perspective is invaluable as this technology continues to reshape our world. Thank you for joining me on this profound exploration.